Tonight, we leave the light of the sun behind and drift into the deep shadows of the solar system. We are traveling to the Kuiper Belt, a silent ring of eternal ice that guards the edge of our home. Welcome to the Orbit for Sleep channel. Let go of gravity and let the quiet darkness carry you gently toward sleep. For much of the 20th century, the outer solar system appeared to be a quiet stretch of space. Neptune marked what seemed to be the final major world, followed by a thin population of dim objects that offered little structure. As telescopes improved, faint points of reflected sunlight began to appear in photographic plates. These detections hinted that the region beyond Neptune might not be empty. Instead, it held a scattered collection of small, frozen bodies that challenged prior assumptions about where the solar system ended. The search for these distant objects grew more systematic during the late 20th century. Observers compared multiple images taken hours apart, looking for subtle movement against the background stars. Motion over such long distances is extremely slow, similar to watching the minute hand of a clock and waiting for confirmation that it has shifted. When researchers compiled the results, a pattern emerged. Many of the detected bodies followed broad, gently curved paths far beyond Neptune's orbit. These trajectories placed them in a region that had not been formally recognized as a structured part of the solar system. As the catalog of detections expanded, the population revealed consistent characteristics. Each object reflected very little sunlight, confirming that their surfaces were coated with dark, icy material. Their temperatures were measured to be hundreds of degrees below the freezing point of water. This placed them in an environment similar to a storage freezer, where chemical activity slows to an extremely low rate. These measurements aligned with theoretical predictions that the early solar system produced leftover fragments that drifted outward and remained preserved cold conditions. The distribution of these bodies suggested a larger underlying structure. When plotted, the objects formed a loose ring around the sun, extending tens of astronomical units beyond Neptune. An astronomical unit, or AU, is the average distance between Earth and the Sunday. Using AU provides scale in regions where kilometers become unwieldy. The extent of this ring indicated that the solar system's boundary was more complex than previously believed. Instead of ending abruptly, it transitioned gradually into a broad zone of frozen debris. Historical models of solar system formation supported this interpretation. During the early stages of planetary growth, countless small bodies collided and merged to form the larger planets. Many fragments, however, were scattered outward by gravitational interactions. Neptune, in particular, played a major role in this process. Its gravity redirected numerous objects into distant orbits where they settled into long-term stability. These survivors became the population that modern telescopes observe today. This frozen frontier also provided insight into the structure of space at extreme distances. Light from the sun weakens dramatically with distance, reducing to a small fraction of its original brightness by the time it reaches these objects. The solar wind, a stream of charged particles emitted by the sun, also loses strength. These gradients create a boundary region where the influence of the sun fades, though not in a single step. Instead, the solar system tapers outward, forming layers shaped by gravity, radiation, and particle flow. The realization that a populated region exists beyond Neptune reshaped our understanding of the solar system's architecture. The outer boundary is not defined by a final planet, but by a complex distribution of ancient material. Each discovery refined the map of this remote zone, revealing a frontier shaped by early planetary dynamics and preserved by extreme cold. This region continues to demonstrate that the solar system is larger, older, and more intricate than its familiar inner worlds suggest. The Kuiper Belt is a wide region beyond Neptune, filled with small, icy bodies that preserve early solar system conditions. Many of these objects never formed into planets and have remained mostly unchanged for billions of years. Their surfaces contain frozen methane, nitrogen, and water ice, offering clues about the materials present around the young Sunday. Unlike the warmer inner solar system, the Kuiper Belt exists in extremely cold conditions where chemical reactions slow down and geological activity remains minimal. These bodies function as natural time capsules. Their surfaces record early solar system chemistry in a way that inner, rocky planets cannot. Systematic observations began in the late 20th century, when sensitive digital detectors revealed faint sunlight reflected by distant objects. Their slow movement across the sky confirmed that they followed stable orbits beyond Neptune rather than behaving like short-lived comet fragments. Spectroscopic studies helped identify their surface materials. Methane ice, carbon monoxide ice, and organic compounds appear frequently. These molecules remain frozen because sunlight at this distance is too weak to warm them. Their preservation indicates that the Kuiper Belt formed in a cold, low-energy environment. The region's structure is shaped by Neptune's gravity. Many objects follow resonant orbits that keep them at predictable distances from the planet. Pluto, for example, completes 2 orbits for every 3 of Neptune. These resonances stabilize motion and prevent close gravitational encounters. The scale of the Kuiper Belt highlights the solar system's extended architecture. It spans dozens of astronomical units, where sunlight has weakened dramatically. A simple comparison uses a flashlight. Standing directly in front of the beam resembles Earth's distance from the sun, while standing far across a field resembles the faint illumination within the Kuiper Belt. Discoveries of large bodies such as Eris in the early 21st century confirmed that Pluto is part of a broader population of similar icy worlds. This reinforced the understanding that the Kuiper Belt is a structured component of the solar system rather than scattered debris. Overall, the Kuiper Belt preserves a record of early planetary evolution. Its objects contain information about the distribution of icy materials, the chemistry of the protoplanetary disk, and the dynamic processes that shaped planetary orbits. Studying this region provides essential context for understanding both our solar system and planetary systems around other stars. The outer edge of the solar system hosts a population of frozen bodies that formed under conditions distinct from those near the Sunday. During the early stages of planetary formation, temperature gradients in the protoplanetary disk determined where different materials could exist in solid form. Close to the Sun, only metals and rocky minerals could condense. Farther out, temperatures dropped enough for volatile compounds, such as water, methane, and nitrogen, to freeze. This created a natural boundary where icy materials accumulated and remained stable. As the young planets grew, Their gravity redistributed surrounding debris. Jupiter and Saturn stirred the inner and middle regions of the disk, scattering many icy fragments outward. Neptune played the most significant role in shaping the population beyond its orbit. Its gravitational influence pushed numerous small bodies into distant, stable trajectories. These objects settled in the cold outer region, where they experienced minimal heating and limited geological change. The physical environment of the solar system's edge reinforces this accumulation. Sunlight weakens dramatically with distance, reducing the energy available to warm or reshape surface material. A simple comparison involves stepping away from a heat source. Near a campfire, warmth is immediate. At a great distance, only a faint trace remains. The Kuiper Belt exists in a zone where solar energy becomes too weak to alter frozen compounds significantly. This preserves both the composition and the structure of the objects that reside there. The orbits of these bodies reflect long-term gravitational interactions. Many follow paths that avoid close encounters with Neptune, maintaining stability over billions of years. Others occupy resonant orbits in which their motion aligns with Neptune's orbital period. These resonances prevent disruptive gravitational influences and contribute to the formation of organized clusters within the region. The presence of frozen worlds at the solar system's edge also aligns with models of disk evolution. Simulations show that the outer disk naturally retains a high proportion of icy debris because the temperature never rose enough to drive these materials away. As the gas of the disk dissipated, the remaining solid fragments stayed in place, forming a broad reservoir of preserved material. This concentration of frozen bodies provides insight into the early solar system. Their composition reflects the distribution of volatile compounds in the protoplanetary disk, while their orbits record the gravitational history of the giant planets. Together, they form a coherent picture of how temperature, distance, and planetary motion shaped the architecture of the outer regions. The accumulation of these ancient frozen worlds serves as evidence of the processes that determined where different types of material could survive and how they were transported during planet formation. The Kuiper Belt occupies a vast region beyond Neptune, and its true extent became clearer only after systematic surveys improved during the late 20th century. Early observations suggested a concentrated band of objects just past Neptune's orbit. As detection methods advanced, astronomers identified bodies at increasingly greater distances, revealing that the belt spans a far wider area than initially assumed. The inner edge begins slightly beyond Neptune, at roughly 30 astronomical units. An astronomical unit, or AU, is the average distance between Earth and the Sun, used as a practical measurement for mapping the solar system. From this inner boundary, the belt stretches outward across a region filled with slow-moving, icy bodies that occupy stable orbits. The distribution is not uniform. Instead, it shows clusters of objects in resonant orbits with Neptune and regions where gravitational interactions have cleared gaps. The main population extends to about 50 AU, where the density of detected objects begins to decrease sharply. This reduction marks the approximate outer edge of the classical Kuiper Belt. Beyond this point, the number of objects drops enough to indicate a transition into a more diffuse region known as the scattered disk. Bodies in the scattered disk follow highly elongated orbits that can reach hundreds of AU from the Sun, shaped by past interactions with Neptune. The measured distances reflect the difficulty of detecting faint objects across immense spans of space. Light from the Sun weakens steadily with increasing distance. At 50 AU, sunlight has only a small fraction of the intensity it has near Earth. A simple comparison involves switching on a lamp in a large room. Standing next to the lamp provides clear illumination, while standing across the room reduces the light to a faint glow. The Kuiper Belt exists in the outer boundaries of this faint glow, making even large objects difficult to detect. Surveys using wide-field digital cameras revealed that the distribution of objects thins significantly beyond 50 AU. This thinning suggested that the protoplanetary disk from which the solar system formed had a natural outer limit. Models of disk evolution support this idea. Gas and dust densities decrease with increasing distance from the Sunday. Beyond a certain point, the disk lacked enough material for significant numbers of icy bodies to form or survive. Although the classical Kuiper Belt ends near 50 AU, the broader structure of the solar system continues outward into the scattered disk and eventually toward the Oort cloud. The Kuiper Belt, therefore, represents one component of a larger system of distant, frozen material that stretches into the far reaches of the Sun's gravitational influence. Understanding the belt's true extent helps clarify the architecture of the solar system. It defines where stable populations of icy bodies reside, where the disk begins to thin, and where more extreme orbits take over. These distinctions reflect the history of planetary formation, the influence of giant planets, and the limits of the material that once surrounded the young Sunday. Pluto's placement within the Kuiper Belt reflects both its physical characteristics and its orbital behavior. When Pluto was discovered in 1930, it appeared to be an isolated object beyond Neptune. As observational techniques improved, astronomers identified many additional bodies in the same region. These discoveries revealed that Pluto is part of a broader population of icy worlds rather than a solitary planet at the solar system's edge. Pluto's composition aligns closely with that of typical Kuiper Belt objects. Its surface contains frozen nitrogen, methane, and carbon monoxide, similar to the ices found on smaller bodies in the region. These materials remain stable only in extremely cold environments. The temperatures in the Kuiper Belt allow volatile compounds to stay frozen, preserving chemical signatures that formed during the early stages of the solar system. Pluto's density, structure, and surface features reflect this environment. Pluto's orbit also connects it directly to the Kuiper Belt. The orbit is elongated and inclined compared to the nearly circular orbits of the major planets. Its path places it in a 3-to-2 resonance with Neptune, meaning Pluto completes 2 orbits for every 3 orbits of Neptune. This resonance prevents close encounters and stabilizes Pluto's motion over long periods. Many smaller Kuiper Belt objects share this orbital pattern, forming a group known as the resonant population. The recognition that Pluto is part of a larger family developed gradually as additional large bodies were discovered. These objects, such as Eris, Haumea, and Makemake, share similar compositions and orbital characteristics. Their presence demonstrated that Pluto is one among several large icy worlds in the region. This broader understanding contributed to the reclassification of Pluto as a dwarf planet during the early 21st century. The change reflected a shift toward describing the solar system based on shared physical and dynamical traits. Historical studies of the protoplanetary disk support Pluto's connection to the Kuiper Belt. Models show that the outer disk contained abundant icy material that coalesced into bodies of varying sizes. Some grew into dwarf planets, while others remained smaller fragments. These objects were influenced by the migration of the giant planets, especially Neptune. As Neptune moved outward, it reshaped the distribution of material and captured certain bodies into resonant orbits. Pluto likely formed in this environment and settled into its current orbital configuration. Pluto's properties, therefore, provide insight into the nature of the Kuiper Belt itself. Its geology includes features such as nitrogen, ice plains, and methane-rich highlands, highlighting the diversity of processes that can occur even in distant, cold environments. The presence of a thin atmosphere that expands and contracts based on its distance from the Sun further illustrates the complexity of outer solar system worlds. Pluto belongs to the Kuiper Belt because it shares the region's defining characteristics: icy composition, resonance-driven orbit, and preservation of early solar system material. Its discovery helped open the path to understanding an entire population of distant, frozen bodies that extend the known boundaries of the solar system. The Kuiper Belt contains a wide range of icy bodies arranged in patterns shaped by both their formation environment and the long-term influence of the giant planets. This distribution is not uniform. Instead, it reflects variations in density, orbital behavior, and the early dynamics of the solar system. Mapping these patterns helps reveal how material was organized in the outer regions during the first stages of planetary development. The highest concentration of objects appears between roughly 40 and 48 astronomical units. Within this band, bodies follow moderately circular orbits that remain stable over long timescales. This region is known as the classical Kuiper Belt. Many objects here show limited orbital eccentricity, indicating that they have not experienced strong gravitational disturbances. Their stability suggests that the outer disk maintained a relatively calm environment compared to the middle regions influenced by the migrations of Jupiter and Saturn. A different distribution appears among resonant populations. These bodies occupy orbits that align with Neptune's orbital period. The most notable group includes objects in a 3:2 resonance with Neptune, a group often referred to as Plutinos because Pluto is the largest member. Resonance locks their motion into predictable timing that prevents close encounters with Neptune. The result is a structured pattern, with clusters forming at specific distances corresponding to stable resonances. Beyond the classical region, the number of objects decreases, and orbital shapes become more elongated. This domain is part of the scattered population, composed of bodies that were pushed outward through past gravitational interactions with Neptune. Their orbits extend much farther into space, sometimes exceeding 100 astronomical units at their farthest points. These distributions trace the history of planetary migration and the transfer of momentum from the giant planets to smaller bodies. The spatial arrangement also reflects the temperature gradient of the early solar system. Cooler regions allowed volatile compounds to freeze and accumulate. As the protoplanetary disk evolved, these icy materials clustered where temperatures remained consistently low. This contributed to the formation of a broad ring of small bodies that retained frozen surfaces long after the inner disk warmed. Wide-field surveys have improved the accuracy of distribution maps. Modern instruments detect faint signals from objects only a few tens of kilometers across. Their positions show the imprint of long-term gravitational shaping, where stable regions remain densely populated and unstable regions contain few or no objects. These gaps resemble patterns seen in planetary ring systems, where gravitational resonances carve structure into otherwise continuous material. The distribution of icy bodies across the Kuiper Belt therefore records multiple layers of solar system history. It preserves information about temperature conditions, early collisions, and the movement of the giant planets. Each region reflects a different combination of environmental and dynamical factors, forming a complex pattern that continues to guide models of solar system evolution. Kuiper Belt objects formed from the outer regions of the protoplanetary disk, a rotating cloud of gas and dust that surrounded the young Sunday. In these distant zones, temperatures were low enough for volatile compounds such as water, methane, and nitrogen to freeze into solid grains. These icy particles collided gently and combined into larger bodies over time. The process resembled the slow accumulation of frost on a cold surface, where small crystals gradually merge into thicker layers. During the early stages of disk evolution, material throughout the outer regions began to clump together. These clumps grew into planetesimals, the building blocks of planets. In the inner system, higher temperatures and stronger collisions led to rapid growth of rocky planets. In the outer disk, lower temperatures and slower motion resulted in a population of icy bodies that grew only to modest sizes. Many of these objects never experienced the conditions necessary to form full planets. The migration of the giant planets played a central role in shaping the origins of the Kuiper Belt. As Jupiter and Saturn shifted positions, they generated gravitational waves that propagated through the disk. These disturbances altered the paths of smaller bodies and pushed some of them outward. Neptune's migration had the strongest effect. As it moved to its current orbit, it scattered nearby objects and redistributed them into stable orbits farther from the Sunday. Many of these objects settled into what is now recognized as the Kuiper Belt. Computer simulations of disk evolution support this sequence. When the giant planets migrate outward, they capture some bodies into resonant orbits and scatter others into elongated trajectories. The surviving objects form a mixture of stable populations and scattered remnants. Their distribution depends on how strongly they were influenced by the shifting gravitational landscape of the early solar system. The chemical composition of Kuiper Belt objects reflects their place of origin. Spectroscopic measurements reveal surfaces rich in ices and complex organic materials. These compounds formed in cold environments and remain preserved because the outer solar system receives limited solar energy. Unlike surfaces on inner planets, which experience melting, erosion, and volcanic activity, the surfaces of Kuiper Belt objects retain the chemical signatures of their formation. Some large Kuiper Belt objects, such as Pluto and Haumea, show evidence of partial differentiation. This process occurs when internal heat allows heavier materials to sink toward the core, while lighter ices rise toward the surface. The heat required for this differentiation likely came from the decay of radioactive elements or from early collisions. These events provide insight into the diversity of conditions that shaped different members of the Kuiper Belt. The origin of Kuiper Belt objects is therefore linked to a combination of cold environmental conditions, slow accretion processes, and the powerful gravitational influence of the giant planets. Their presence preserves a record of the early solar system, offering clues about how materials were distributed, how planets migrated, and how small bodies survived the dynamic evolution of the protoplanetary disk. Resonances with Neptune shape a significant portion of the Kuiper Belt structure. A resonance occurs when two bodies orbit the Sun in a repeating numerical ratio. This alignment creates predictable gravitational interactions that stabilize or destabilize certain orbits. In the outer solar system, Neptune's mass and position allow it to influence objects far beyond its immediate surroundings. The most well-known resonance is the 3-2 resonance, occupied by Pluto and a large group of smaller bodies, often called Plutinos. An object in this resonance completes 2 orbits for every 3 orbits of Neptune. Despite crossing Neptune's orbital path, these bodies never come close enough to the planet to experience disruptive encounters. The timing of their orbits prevents such interactions, allowing long-term stability. This pattern is similar to 2 gears with different sizes rotating in sync, so their teeth never collide. Other resonances appear throughout the Kuiper Belt. Objects in the 2-1 resonance, for example, complete 1 orbit for every 2 of Neptune's. These bodies occupy more distant regions and often follow moderately elongated paths. Resonances of higher order, such as 5-2 or 7-4, also appear, each forming clusters of objects at specific distances. The presence of these clusters maps the gravitational landscape shaped by Neptune's migration. These resonant populations formed during the early evolution of the solar system. As Neptune moved outward, it swept through regions of the protoplanetary disk. Bodies that encountered the moving resonance zones were captured into stable orbital relationships. Computer simulations reproduce this process, showing that migrating giant planets naturally create resonant families of small bodies. The resulting distribution matches the patterns observed in modern surveys. Resonances also contribute to gaps in the Kuiper Belt, regions where orbits experience repeated gravitational kicks from Neptune become unstable. Objects in these zones eventually scatter into new trajectories or leave the belt entirely. This mechanism creates empty intervals that resemble the gaps within Saturn's rings, where resonances with moons carve distinct structures. The effect of resonances extends beyond orbital mechanics. Stability within resonances allows objects to survive for billions of years, preserving material from the early solar system. Their compositions and surface properties offer clues about the environment in which they formed. Meanwhile, objects pushed out of unstable regions trace the history of gravitational interactions and planetary migration. Neptune's resonances therefore serve as a framework for understanding the Kuiper Belt's complex architecture. They reveal how a single planet can organize distant material into ordered structures, shaping both the distribution and long-term evolution of small bodies at the edge of the solar system. Kuiper Belt objects move through space on orbits that are both slow and widely spaced. These trajectories arise from the enormous distances between the Sun and the outer regions of the solar system. Because gravitational force weakens with distance, objects far from the Sun experience only a gentle pull. This creates long orbital periods and reduces the speeds at which these bodies travel. An everyday comparison is the difference between a ball held close to a magnet and one held far away. The closer ball reacts strongly, while the distant one moves slowly and responds only weakly. A typical Kuiper Belt object requires hundreds of years to complete a single orbit. Its motion across the sky is subtle, shifting only slightly over many nights of observation. These slow paths reveal information about the distribution of mass in the outer solar system. Even small deviations in motion can indicate the presence of resonances, gravitational encounters, or the lingering effects of migration by Neptune and the other giant planets. The wide spacing between orbital paths reduces the frequency of collisions. In the inner solar system, crowded conditions during early formation led to frequent impacts that contributed to planetary growth. In the Kuiper Belt, the greater separation between objects produced fewer collisions, resulting in a population of bodies that retain their original shapes and structures. Many objects remain irregular and lightly processed, preserving the physical record of their formation environment. Orbital eccentricity varies across the Kuiper Belt. Some objects follow nearly circular paths, indicating a history of gentle gravitational shaping. Others possess elongated orbits, stretching tens of astronomical units between their closest and farthest points from the Sun. These elongated orbits often trace back to gravitational scattering events, where Neptune's movement pushed objects into new trajectories. The pattern of eccentricities across the belt reflects the combined effects of stability, resonance, and past disturbances. Inclination also plays a role in the region's dynamics. Many Kuiper Belt objects orbit close to the plane of the solar system, similar to the planets. A separate group follows orbits that tilt at significant angles. These high-inclination bodies likely experienced strong gravitational interactions, lifting them above or below the typical orbital plane. Their presence shows that the outer solar system includes a mixture of dynamically calm and dynamically excited populations. Together, these orbital characteristics create a detailed picture of how small bodies behave at great distances. Slow speeds, wide separations, varied eccentricities, and diverse inclinations record billions of years of gravitational influence. The dynamics of these orbits help explain why the Kuiper Belt preserves material left over from the early solar system, and how the region continues to revolve under the gentle but persistent pull of the Sun and Neptune. The Kuiper Belt contains objects that formed and evolved in extremely cold conditions. At distances beyond 30 astronomical units, sunlight weakens to a small fraction of the energy received by Earth. This limited energy supply keeps surface temperatures far below the freezing point of water. Measurements from spacecraft and telescopic observations indicate that many Kuiper Belt objects maintain temperatures near -220 degrees Celsius. At such temperatures, volatile compounds that would evaporate closer to the Sun remain frozen and stable. The composition of these distant worlds reflects the environment of the early solar system, Spectroscopic studies reveal surfaces rich in ices, including water ice, methane ice, nitrogen ice, and carbon monoxide ice. Complex organic materials also appear, produced either by radiation-induced chemical reactions or preserved from the earliest stages of formation. On Earth, methane exists primarily as a gas or liquid fuel, and nitrogen forms the bulk of the atmosphere. In the Kuiper Belt, both remain frozen into solid layers because the environment lacks sufficient heat to alter their physical state. These compounds accumulate in patterns shaped by temperature and solar radiation. Water ice forms the structural base of many objects, creating a rigid framework that supports other materials. Methane and nitrogen ices often coat the surface, creating bright or reflective patches. The presence of these ices explains the varying colors of Kuiper Belt objects, which range from neutral gray to deep red. The reddest surfaces contain complex organic molecules known as tholins, formed when radiation modifies simple carbon-rich compounds over long periods. Low temperatures also slow geological activity. Inner planets experience erosion, tectonics, and volcanic processes driven by internal heat and solar energy. Kuiper Belt objects lack such energy sources, so their surfaces change primarily through impacts from micrometeoroids or slow sublimation of volatile ices. The limited activity allows ancient features to remain preserved. Craters, fractures, and frozen plains record conditions that have persisted for billions of years. Some larger Kuiper Belt objects show signs of internal differentiation, meaning their interiors separated into layers of rock and ice. This process requires heat, likely produced by the decay of radioactive elements or the energy released during early collisions. Differentiation leaves behind evidence such as smooth plains or subtle variations in density. Even so, the cold environment prevents extensive resurfacing, allowing these structures to remain largely intact. The distribution of materials across the Kuiper Belt reflects the thermal structure of the early protoplanetary disk. Regions closer to the Sun lost volatile materials due to higher temperatures, while the outer disk retained them. The objects that formed in this environment preserved a record of the chemical composition available at great distances. Their surfaces act as frozen archives, storing information about the building blocks present during the formation of the solar system. The temperatures and compositions of these distant worlds therefore provide essential clues to the conditions that shaped the outer solar system. Their frozen surfaces, diverse materials, and minimal geological changes reveal how environment influences planetary development and how ancient chemical signatures can persist over cosmic timescales. The Kuiper Belt preserves material from the early solar system, and its formation influenced the development of the planets. During the earliest stages of disk evolution, the outer regions held large quantities of icy particles and dust. These materials accumulated slowly, forming small bodies that later became the population of Kuiper Belt objects. Their presence indicates that the outer disk contained enough mass to participate in shaping the solar system's structure, even though it did not produce additional large planets. The growth of the giant planets altered the distribution of material across the disk. Jupiter and Saturn formed quickly and began clearing gaps around their orbits. Their gravity redistributed nearby debris, pushing some of it outward toward Neptune's region. As Neptune grew, it interacted with these materials, capturing some into resonant orbits and scattering others farther from the Sun. These interactions contributed to the formation of the Kuiper Belt as a stable reservoir of icy bodies. The movement of Neptune played a particularly significant role. Models of planetary migration suggest that Neptune originally formed closer to the Sun. As it drifted outward, it passed through regions filled with smaller bodies. This movement gravitationally disturbed these objects, driving some into the inner solar system while placing others into stable, distant orbits. The final configuration of the Kuiper Belt reflects these events, marking the zones where Neptune's influence shaped long-term orbital patterns. Material scattered from the outer disk also contributed to early collisions within the solar system. Some objects were redirected toward the inner regions, where they delivered volatile compounds such as water and organic molecules. This influx of material helped establish the chemical inventory of the young Earth and other rocky planets. The presence of similar volatile compounds in Kuiper Belt objects today supports the idea that they were among the carriers of these early ingredients. The distribution of Kuiper Belt objects provides clues about the density and temperature structure of the ancient disk. Regions closer to the Sun lost volatile materials due to higher temperatures, while the outer disk retained them. The objects that formed in these colder regions preserve these volatile-rich compositions. Their existence confirms that the protoplanetary disk extended far beyond the orbits of the giant planets and contained gradients that influenced where different materials accumulated. The Kuiper Belt also records the decline of the protoplanetary disk. As the disk's gas dissipated, small bodies lost the drag forces that once shaped their orbits. Their trajectories became dominated by gravitational interactions alone. This transition allowed resonant populations and scattered groups to stabilize into the configurations observed today. The diversity of these groups reflects the different dynamical pathways that objects experienced during the disk's final stages. In this way, the Kuiper Belt shaped the early solar system by storing remnant material, tracing the movements of the giant planets, supplying volatiles to the inner worlds, and preserving the conditions of the protoplanetary disk. Its structure serves as a record of the processes that formed the planets and determined the architecture of the solar system. The Kuiper Belt plays a central role in supplying the solar system with short-period comets. These comets follow orbits that return to the inner solar system on timescales shorter than 200 years. Their origins trace back to the population of icy bodies that occupy stable or moderately disturbed orbits beyond Neptune. Understanding how these comets travel inward reveals the dynamic link between the outer and inner regions of the solar system. Kuiper Belt objects contain large amounts of volatile material, including frozen water, methane, and carbon monoxide. These compounds remain stable in the cold, outer regions. When an object is displaced from its distant orbit and moves closer to the Sun, sunlight begins to warm its surface. The frozen volatiles transition directly from solid to gas, producing jets of vapor that release dust and form the characteristic cometary coma and tail. The presence of these volatile-rich materials makes Kuiper Belt objects natural candidates for comet formation. Gravitational interactions initiate the movement of these bodies toward the inner solar system. Neptune exerts the strongest influence. Objects that drift into unstable regions near Neptune's orbit can receive gravitational nudges that alter their paths. Some are pushed outward into the scattered disk, while others are redirected inward. When an object adopts a new trajectory with a closer approach to the Sun, it can evolve into a short-period comet. The redistribution of these bodies reflects the long-term patterns of Neptune's migration and the gravitational structure of the outer solar system. Computer models of orbital evolution support this mechanism. Simulations show that resonant and scattered populations regularly transfer objects inward over millions of years. Once these bodies enter the planetary region, interactions with Jupiter and Saturn often reshape their orbits further. These changes shorten the orbital period and lock the comet into a more predictable path. Many well-known comets follow orbits consistent with this process, linking their behavior to the distant Kuiper Belt. Observations of comet composition provide additional evidence for this connection. Spectroscopic measurements detect water vapor, carbon-bearing molecules, and other volatiles typical of Kuiper Belt surfaces. The chemical signatures of comets closely match the ices present on distant objects, reinforcing the idea that both formed under the same cold conditions. The similarity indicates that comets preserve material from the outer solar system, largely unchanged since their formation. The delivery of comets to the inner solar system has influenced planetary surfaces. Impacts during earlier epochs supplied additional water and organic molecules to Earth and other rocky planets. These events helped shape their chemical inventories. Some theories propose that a portion of Earth's early water originated from cometary material. While this remains debated, the volatile content of comets demonstrates that they acted as carriers of essential compounds. The Kuiper Belt's role as a comet reservoir reveals the dynamic interplay between distant icy bodies and the inner solar system. It shows how gravitational forces gradually redirect ancient material inward, where it interacts with planets and leaves physical evidence of its passage. This connection underscores the importance of the Kuiper Belt as both a preserved archive and an active component of the solar system's ongoing evolution. Kuiper Belt objects contain material that formed under the cold conditions of the early solar system, and their preserved compositions provide insight into processes that shaped Earth during its earliest stages. Because these bodies have remained largely unchanged for billions of years, they act as reference points for understanding the chemical environment from which the planets emerged. During the formation of the solar system, volatile compounds such as water, methane, ammonia, and carbon dioxide condensed in the outer regions of the protoplanetary disk. These compounds froze onto small grains of dust, forming the building blocks of Kuiper Belt objects. The same classes of materials eventually contributed to the mixture of ices and gases that influenced Earth's early atmosphere and surface chemistry. The preserved compositions of distant objects, therefore, provide a baseline for reconstructing the original inventory of volatile compounds available to the young Earth. Spectroscopic studies of Kuiper Belt surfaces reveal specific molecular signatures that match those observed in comets. These signatures include water ice, carbon-bearing molecules, and simple organic compounds. Comets transported similar materials into the inner solar system, where they impacted Earth during its early history. This influx delivered additional volatiles, and may have contributed to the development of the early atmosphere. The chemical similarities between Kuiper Belt objects and comets support the idea that the outer solar system acted as a reservoir for the substances introduced to Earth through impacts. The orbital histories of Kuiper Belt objects also provide context for understanding major events in Earth's early evolution. Models of planetary migration show that shifts in the orbits of Jupiter and Saturn destabilized portions of the outer disk. This process redirected icy bodies inward, increasing the rate of impacts throughout the solar system. Geological evidence on Earth, the Moon, and other rocky bodies records periods of elevated impact activity consistent with these models. The structure of the Kuiper Belt helps constrain the timing and magnitude of these events by revealing how material was redistributed during planetary migration. The study of Kuiper Belt compositions helps researchers determine whether certain elements or molecules found on Earth originated from local processes or were delivered from distant regions. For example, isotopic ratios, measurements that compare different forms of an element, provide clues about the sources of water and organic molecules. Some isotopic ratios observed in Kuiper Belt-linked materials resemble those found in Earth's early geological record. These similarities indicate that at least part of Earth's volatiles came from primitive objects formed far from the Sunday. Kuiper Belt objects also shed light on the thermal and chemical gradients of the ancient protoplanetary disk. The survival of volatile-rich materials at great distances confirms that temperature played a key role in determining which compounds could persist. By comparing these preserved materials with those found on Earth and other rocky planets, researchers can reconstruct the environmental conditions that shaped planetary formation, atmospheric development, and early chemical evolution. In this way, distant icy bodies reveal how Earth acquired its initial complement of volatiles and how large-scale movements within the early solar system affected the flow of material. Their preserved surfaces and stable compositions serve as records of processes that influenced Earth long before its modern environment emerged. The chemical makeup of Kuiper Belt objects reflects conditions that existed in the early solar system, and these preserved materials offer insight into the ingredients relevant to the origin of life. Their surfaces contain volatile ices and organic compounds that formed in cold environments. These compounds remain stable for billions of years due to the extremely low temperatures beyond Neptune. Because the Kuiper Belt retains these early chemical signatures, it provides a record of substances that may have influenced prebiotic chemistry on Earth. Spectroscopic studies reveal that many Kuiper Belt objects contain mixtures of water, ice, methane, nitrogen, carbon monoxide, and complex organic materials. On Earth, such organic materials play essential roles in biological systems. In the outer solar system, they form through slow chemical reactions driven by ultraviolet radiation or energetic particles. These processes modify simple carbon-based molecules into more complex structures. Similar pathways contributed to the formation of organic material found in meteorites and comets that impacted the early Earth. Comets linked to the Kuiper Belt serve as carriers of these compounds into the inner solar system. When they approach the Sun, warming releases gas and dust from their surfaces. These particles contain water and organics that resemble materials found on Kuiper Belt objects. Impacts from such comets may have delivered additional sources of carbon, nitrogen, and hydrogen to the young Earth. Although Earth possessed its own internal inventory of volatiles, external delivery played a complementary role in shaping the early chemical environment. Isotopic measurements provide further connections. Ratios of specific isotopes in cometary water and organic compounds often resemble those detected in materials associated with the Kuiper Belt. These similarities suggest that certain elements essential to early chemistry originated, at least in part, from distant icy bodies. Comparing these signatures with Earth's earliest geological record helps researchers trace the pathways through which key ingredients for life reached the planet. The stability of frozen compounds in the Kuiper Belt offers additional insight. Because temperatures remain extremely low, chemical processes proceed slowly, preserving ancient molecular structures. Studying these preserved materials helps scientists reconstruct the composition of the protoplanetary disk and identify which compounds were available during the formation of the planets. This information clarifies how chemical gradients in the disk influenced the distribution of materials necessary for life. The variety of compounds present in the Kuiper Belt shows that organic chemistry can develop in cold, low-energy environments. This finding supports the broader idea that prebiotic chemistry does not require warm conditions alone. It also suggests that other planetary systems with similar outer belts could contain reservoirs of organic material. Such regions may contribute to the chemical diversity available for potential life-bearing worlds. In this way, the chemistry of Kuiper Belt objects helps connect the distant outer solar system to the conditions that shaped early Earth. The preserved ices and organics found on these bodies provide a window into the chemical environment that supported the emergence of life and offer clues about how similar processes might occur elsewhere in the galaxy. Reaching the Kuiper Belt requires spacecraft to travel far beyond the orbits of the giant planets. Modern missions rely on precise navigation, long-term planning, and careful use of gravitational assists to cover these distances. The New Horizons mission provided the clearest demonstration of this approach. Launched in 2006, it used a gravity assist from Jupiter to gain speed, reducing travel time to Pluto and the surrounding region. A gravity assist functions by transferring momentum between a spacecraft and a planet. When a spacecraft approaches a planet and swings past it, the planet's gravity accelerates the spacecraft and alters its trajectory. An everyday analogy involves a moving train. If a person runs alongside and jumps onto it, the motion of the train gives them additional speed. In space, this technique allowed New Horizons to reach the Kuiper Belt much faster than a direct path would have permitted. After the Jupiter assist, New Horizons continued outward on a trajectory that intersected Pluto's orbit. The spacecraft entered the Kuiper Belt region in 2015, providing detailed measurements of surface composition, temperature, and atmospheric structure. Data from this flyby confirmed the presence of nitrogen ice plains, methane-rich highlands, and a thin atmosphere that expands when Pluto receives sunlight. These observations offered the first close-up view of a Kuiper Belt object and demonstrated the scientific potential of exploring the region directly. Following the Pluto encounter, mission planners identified additional targets within the Kuiper Belt. The spacecraft performed trajectory adjustments using small thrusters to intercept Arrokoth, a distant object in the classical belt. The flyby in 2019 revealed a contact binary structure, indicating that Arrokoth formed through gentle mergers rather than violent collisions. Its smooth surface and uniform composition provided insight into the calm conditions of the early solar system, where icy particles accumulated slowly. Long-duration missions to the Kuiper Belt require reliable power sources. Because sunlight is weak beyond 30 astronomical units, spacecraft rely on radioisotope thermoelectric generators. These devices convert heat from radioactive decay into electricity, supplying power for instruments and communication. The steady, long-lasting energy output allows spacecraft to operate for decades as they travel through regions where solar panels are ineffective. Communication also becomes increasingly difficult with distance. Signals take several hours to travel between Earth and a spacecraft in the Kuiper Belt. Engineers compensate by sending commands long in advance and designing spacecraft that operate autonomously. Large antennas on Earth receive the faint returning signals, which contain scientific data gathered during flybys. Modern missions have shown that reaching the Kuiper Belt is technically feasible and scientifically rewarding. The combination of precise navigation, gravitational assists, and durable engineering enables spacecraft to explore regions once considered unreachable. These missions expand understanding of the outer solar system and demonstrate how distant, icy worlds fit within the larger picture of solar system evolution. The Kuiper Belt occupies the transitional region between the planetary zone and the far outer reaches of the solar system. Beyond its outer edge, the density of objects decreases sharply, but gravitational influences continue to shape trajectories over great distances. These conditions mark the beginning of the pathway toward the Oort cloud, a vast, spherical reservoir of icy bodies that extends thousands of astronomical units from the Sunday. The Kuiper Belt and the Oort cloud trace back to similar origins. Both formed from material in the protoplanetary disk, yet each region reflects different outcomes of early gravitational processes. Objects that remain near the plane of the solar system and experience moderate interactions with the giant planets settled into the Kuiper Belt. Others encountered stronger gravitational disturbances that pushed them into distant, highly elongated orbits. Over time, these orbits expanded into the broad sphere that defines the Oort cloud. Computer simulations of solar system formation demonstrate how small differences in orbital encounters can determine whether a body becomes part of the Kuiper Belt or is ejected toward the Oort cloud. For example, a planetesimal that experiences repeated scattering by Neptune may eventually reach a trajectory that carries it thousands of astronomical units from the Sunday. Once placed at such distances, the Sun's gravitational pull weakens to the point that nearby stars and the galactic tide begin to shape its long-term orbit. The Kuiper Belt, therefore, acts as an intermediate region where objects transition between stable, near-plane orbits and the distant isotropic distribution characteristic of the Oort cloud. Some bodies in the scattered disk already follow elongated paths that extend far beyond the classical Kuiper Belt. These orbits represent a continuum leading toward the outermost reservoir. The scattered disk is thus considered the inner source region from which the Oort cloud gradually developed. Observations of long-period comets support this framework. Their orbits approach the Sun from all directions, indicating origins far beyond the Kuiper Belt. Yet their compositions resemble the ices found on Kuiper Belt objects. This similarity suggests a shared heritage, with the Kuiper Belt representing the population that remained close, while the Oort cloud contains bodies displaced much farther by early gravitational interactions. Understanding the connection between these regions clarifies the overall structure of the solar system. The Kuiper Belt outlines the disk-shaped outer boundary shaped by planetary dynamics, while the Oort cloud marks the transition to the Sun's extended gravitational domain. These components form a layered system in which material moves gradually outward over long timescales. The concept of the Kuiper Belt as a gateway emphasizes that the solar system does not end abruptly. Instead, it tapers outward through zones of decreasing density and increasing dynamical complexity. This structure reflects the cumulative effects of planetary migration, stellar encounters, and galactic influences that acted over billions of years. The Kuiper Belt serves as a reference point for understanding similar structures around other stars. Many planetary systems contain regions where icy bodies accumulate beyond the reach of strong stellar heating. These regions, often called debris belts or planetesimal belts, form under conditions that parallel those of the early solar system. Comparing the Kuiper Belt with these extrasolar belts helps clarify how common such structures are and how they contribute to the development of planets. Observations from infrared telescopes reveal that numerous stars possess cold outer belts composed of dust and frozen material. These belts emit faint infrared light because their particles absorb starlight and re-radiate it at longer wavelengths. The brightness and distribution of this emission allow researchers to estimate the size, temperature, and density of the belts. Some systems show sharp outer rings, while others display broad, diffuse regions similar to the Kuiper Belt. The formation of these belts follows patterns consistent with protoplanetary disk evolution. In young systems, dust and icy grains collide and merge into larger bodies. These bodies gradually accumulate into populations of planetesimals. Collisions among these objects produce dust that replenishes the belts over time. The balance between accumulation and fragmentation maintains the belt's structure and helps identify its age. Younger belts tend to be brighter, while older belts resemble the more diffuse structure of the Kuiper Belt. The presence of planets strongly influences the shape and distribution of extrasolar ice belts. In some systems, planets carve gaps or create distinct rings within the belt. Their gravitational interactions shape the orbits of nearby material, similar to how Neptune organizes resonant populations in the Kuiper Belt. High-resolution images of several nearby systems show arcs, asymmetries, and clumps that reflect the gravitational influence of unseen planets. Comparisons across systems demonstrate that outer belts vary widely in scale. Some extend only a few tens of astronomical units from their star, while others span several hundred. These differences provide insight into the mass and temperature profiles of the original disks. Stars with higher luminosity tend to have belts located farther out, since the region where ices can remain stable lies at greater distances. This parallels the solar system, where the Kuiper Belt begins just beyond Neptune, marking the zone where volatile compounds can freeze. Studying extrasolar belts also helps identify the potential for comet production in other systems. Dusty outer belts, composed of volatile-rich bodies, can supply comets to inner regions, influencing planetary atmospheres and surface chemistry. This process mirrors the role of the Kuiper Belt in generating short-period comets. Systems with active comet populations may experience more frequent delivery of water and organic material, contributing to conditions that support habitability. Through these comparisons, the Kuiper Belt becomes part of a broader context in planetary science. Its structure and behavior reflect universal processes that occur in many young planetary systems. Understanding how ice belts form, evolve, and interact with planets helps clarify how common the features of our own solar system may be within the galaxy. Kuiper Belt objects follow stable or moderately disturbed orbits shaped by the gravitational influence of the giant planets. Over billions of years, these orbits gradually evolve, revealing the long-term pathways available to bodies in the outer solar system. The fates of these objects depend on factors such as orbital resonance, gravitational encounters, and the slow influence of the galactic environment. Objects in stable regions of the classical Kuiper Belt tend to persist for extremely long periods. Their nearly circular orbits keep them at safe distances from Neptune, minimizing disruptive gravitational interactions. These bodies can remain in the Kuiper Belt for the entire lifespan of the solar system. Their stability reflects the calm, dynamical conditions that exist in certain regions beyond Neptune. Other populations follow less stable trajectories. Resonant objects, such as those in the 3-2 or 2-1 resonances with Neptune, experience periodic gravitational interactions. Although these resonances protect them from close encounters, small shifts in orbital parameters can accumulate over time. Some objects may eventually drift out of resonance and enter more chaotic orbital zones. Once there, they can be scattered inward or outward, depending on the nature of the encounter. The scattered disk contains objects with highly elongated orbits. Their paths carry them tens or even hundreds of astronomical units from the sunday. Each time these bodies return to the inner edge of their orbit, they encounter Neptune's gravitational field. These periodic interactions gradually modify their trajectories. Some are pushed outward toward the distant regions where the Oort cloud begins. Others are redirected inward and may evolve into short-period comets. Over very long time scales, the galactic environment also plays a role. The Sun orbits the center of the Milky Way and experiences subtle gravitational influences from passing stars and the galactic tide. These weak but persistent forces can alter the orbits of distant bodies, particularly those already on elongated paths. Such interactions may lift objects into higher inclinations or adjust their orbital distances, contributing to the gradual exchange of material between the Kuiper Belt, the scattered disk, and the outer reservoirs of the solar system. Collisions represent another possible fate, though they are rare due to the wide spacing between objects. When impacts do occur, they can fragment bodies into smaller pieces or modify their rotational states. Some large Kuiper Belt objects show evidence of past collisions, such as irregular shapes or families of fragments that share similar orbits. A small number of Kuiper Belt objects may eventually escape the solar system entirely. Repeated gravitational kicks from Neptune or interactions with resonances can place them on trajectories that exceed the Sun's escape velocity. These objects drift into interstellar space, becoming unbound remnants of the solar system's early formation. The long-term evolution of Kuiper Belt objects therefore reflects the combination of stability, gradual perturbation, and occasional dramatic shifts. Their fates illustrate the ongoing dynamical processes that continue to shape the outer solar system across billions of years. The Kuiper Belt preserves physical and chemical conditions that reflect the earliest phases of planet formation. Its objects formed in the cold outskirts of the protoplanetary disk, where temperatures were low enough for volatile compounds to freeze. Because these bodies experience minimal heating and limited geological activity, they retain the composition and structure of the primordial disk. Their properties help reconstruct the processes that governed how material accumulated into planets. The distribution of Kuiper Belt objects reveals gradients in temperature and density across the ancient disk. Regions closer to the Sun held warmer material, allowing only metals and silicates to condense. Farther out, water, methane, nitrogen, and carbon monoxide froze into solid grains. These grains merged into icy planetesimals. The coexistence of rocky inner planets and icy outer bodies demonstrates how temperature shaped the architecture of the solar system. The Kuiper Belt serves as the boundary where volatile materials could remain stable and participate in planetesimal growth. Orbital patterns within the belt record the influence of giant planet migration. As Jupiter, Saturn, Uranus, and Neptune shifted positions during the early solar system, their gravity redistributed surrounding material. Neptune's outward movement was especially significant. It captured some bodies into resonant orbits and scattered others into distant trajectories. These processes sculpted the Kuiper Belt into the structured region observed today. The pattern of resonant objects and scattered populations provides evidence for the timing and scale of planetary migration. Surface compositions of Kuiper Belt objects also provide insight into early chemical evolution. Spectroscopic studies reveal mixtures of water ice, methane ice, nitrogen ice, and complex organic compounds. These materials originally formed through radiation-driven reactions on small dust grains. Their preservation indicates that early chemical processes occurred throughout the disk, not only in regions close to the Sunday. Similar compounds appear in meteorites and comets that impacted the inner planets, supporting the idea that the outer disk contributed essential volatiles during planetary development. Internal structures of larger Kuiper Belt objects show that some underwent partial differentiation. This process occurs when internal heat allows denser materials to sink toward the center, while lighter ices rise toward the surface. Differentiation requires energy from radioactive decay or early collisions. Its presence in some objects, but not others, suggests diversity in the thermal histories of planetesimals. This diversity reflects variations in formation, time, size, and collisional environment across the outer disk. The overall distribution of masses within the Kuiper Belt helps constrain models of how quickly planetesimals formed. The presence of large bodies such as Pluto, Eris, and Makemake indicates that significant growth occurred before the disk dissipated. At the same time, the abundance of smaller objects suggests that not all material aggregated into larger worlds. This mixture supports the idea that planet formation involved both rapid, early growth and long periods of slow accumulation. Through its composition, orbital structure, and physical diversity, the Kuiper Belt provides a detailed record of the processes that shaped planetary formation. It reveals how temperature influenced material distribution, how giant planets reshaped the disk, and how small bodies preserved chemical signatures from the earliest stages of the solar system. The Kuiper Belt defines a transitional zone where the structured architecture of the planetary system begins to dissolve into the wider gravitational domain of the Sunday. This region marks the point at which familiar patterns, circular orbits, ordered planetary spacing, and clear dynamical boundaries give way to less predictable trajectories and decreasing material density. The diminishing influence of the Sun in this area provides a physical marker that has long informed attempts to understand the limits of the solar system. As distance from the Sun increases, gravitational control weakens. Kuiper Belt objects orbit slowly and experience perturbations from both the giant planets and the galactic environment. Their behavior demonstrates that the solar system does not end abruptly, but instead transitions gradually into interstellar space. This fading influence forms a natural boundary where the concept of a planetary system begins to blur. The structure of the Kuiper Belt thus illustrates how astronomical systems possess diffuse edges rather than sharp borders. Beyond the Kuiper Belt lies the scattered disk, followed by the Oort cloud. These regions contain bodies whose orbits extend thousands of astronomical units and are shaped more by external forces than by the Sun alone. The existence of these distant reservoirs challenges narrow definitions of the solar system. Instead of a compact arrangement of planets, the solar system becomes a layered structure where small bodies trace the gradual decline of solar gravity. This layered configuration reflects the interplay between local and galactic influences. The Kuiper Belt also raises questions about how structure emerges from the early processes of planetary formation. Its objects preserve the conditions of the primordial disk, while their current distribution records the migrations of the giant planets. The boundary represented by the Kuiper Belt, therefore, marks both a physical limit and a historical transition. Inside this region, planetary formation produced well-defined worlds. Beyond it, the disk thinned, collisions became rare, and small bodies remained largely unchanged. The contrast between these environments highlights how changes in temperature, density, and dynamical activity shape the architecture of planetary systems. In studying the Kuiper Belt, astronomers also confront broader questions about classification and identity. Pluto's redefinition as a dwarf planet illustrated the difficulty of applying categorical labels to objects that occupy transitional zones. The boundary represented by the Kuiper Belt is not only physical, but conceptual. It forces reconsideration of what constitutes a planet, how systems should be defined, and where meaningful edges can be drawn in environments that evolve over billions of years. The gradual fading of order at the edge of the solar system mirrors patterns observed throughout the galaxy. Planetary systems around other stars also display belts of debris, extended reservoirs of icy bodies, and diffuse outer regions where central gravitational control diminishes. The Kuiper Belt therefore fits within a broader context, serving as an example of how large-scale systems transition into wider cosmic environments. By examining the outer edge of the solar system, researchers gain insight not only into the physical limits of planetary formation, but also into how boundaries function in complex, evolving systems. The Kuiper Belt stands as a reminder that edges in astronomy are rarely abrupt. Instead, they mark regions where structure transforms gradually into the broader expanse of the galaxy.